is 15 amps and the angular frequency is 120 pi radians per second. So this is 15 amps times the sine of 120 pi t. Right? And the resistance of the loop is 2 ohms. So that's the resistance of the loop that's over here. If you like, let's put a resistor like that, and that's 2 ohms. Okay. First question. What is the current induced in the rectangular loop at t is equal to 0? Let's see if one of these work. Well, what will be the current? What should I start with? The current should be what? I want the induced current. How do I get the magnitude of the induced current?
Should be the derivative of the magnetic flux.
That's something else. That's not the induced current. How do you get current? Ohm's law. You want the current? Ohm's law. Voltage divided by the resistance. But what is the voltage? That's the EMF. That's the one with the derivative of the magnetic flux with respect to time. So know what you need to know to get started. So you say, okay, the current, Ohm's law. Voltage divided by resistance. So what is voltage? It's going to be the induced voltage. And this chapter is teaching you induced voltage, called the induced EMF, which by Faraday's law is d phi dt. And there's a minus sign in there, and you can either work with it in the beginning or depending on how the question is phrased. But not bad. So this is the EMF divided by the resistance. The question is, what's the EMF? It's minus the derivative of the flux with respect to time. But the minus sign, I can either not even put it in there, right? The only time I'm going to use the minus sign is to figure out the direction of the current, of the induced current, right? Do not confuse this current over here, right? This current is not the induced current. This is set up by whatever, some function generator, right? Some function generator that puts out a sine curve. This long wire has a function generator connected to it, which and the output of the function generator, is that wiggle. That's the button that you press, and the voltage is going to be the voltage amplitude times the sine of omega t. And then this thing has some resistance, whatever, and the current in there is going to be that voltage in it divided by that resistance, right? And this one will be like delta V naught sine of omega t divided by r, and this you define as the amplitude. But instead of giving you how you get it, they're just giving you what it is. Right? So there is a voltage, there's a voltage that's driving current in this long wire, and the current just happens to be this. But notice that this current in this wire is time dependent. So it generates a magnetic field over here. Actually, everywhere over here, everywhere around this wire, there is a magnetic field generated by this current. But because this current is changing with time, the magnetic field that it generates is changing with time. And as that magnetic field through this loop changes with time, the magnetic flux through this loop is going to change with time. And as the magnetic flux through this loop changes with time, there will be an induced EMF, which is what this is. Right? This is an induced voltage. EMF, you can call it like that, or just that, or V induced. Right? So as this current changes, as time goes on, the resulting magnetic field that it produces will be changing as time goes on, and as the magnetic field through this region is changing as time goes on, the magnetic flux through it is going to be changing as time goes on. And that changing magnetic flux will lead to an induced voltage in that loop. And this is what Faraday's law is going to give me. Right? So Faraday's law is this. The minus sign is to tell me something about the direction of the induced current, which is to oppose the change in the flux produced by this other current. But anyway, what was the first question? What is the current induced in the loop at t is equal to 0? Okay, so I want to know what is the induced current, right, in this loop. Right, so the induced current is the induced EMF, if you want to call it like that, divided by the resistance, right? But that induced, well, is the same as this, right? It's the derivative of the magnetic flux with respect to time, and then the minus sign is just to tell me something about, the direction of the current. Anyway, what is the magnetic flux through this loop? How do I figure out the magnetic flux through this loop? Is the magnetic field the same everywhere? No, it's going to be changing, right? So what I need to do is figure out the magnetic field at some distance r. Let's say at this distance r from the wire that's producing it. So the magnetic field there will be mu naught I divided by 2 pi r, where r is this distance. And if I consider a small increase in r, an infinitesimal length r, which is small compared to r, it's just that I'm making it over there a little big so that you can see it. What is the area of this strip of, did they give us the length of that thing? They called it 8 centimeters. How about I call it, we call this L. What is the area of that strip? LDR, right? So what will be the magnetic flux through that strip? It's called d phi or d phi. What's the magnetic flux through that strip? What would it be? What should I write down?
Mu naught I over 2 pi r times LDR.
So what should I start with? Right away, what should I be thinking? And then we'll plug in stuff in.
B cross A.
It would be the magnetic field there times that area, right? Right? And then that magnetic field is this. And this is the, so that's D flux. And this current is this. So that the magnetic flux through that strip is mu naught, and then the current is, I can call it I naught if you like, sine of omega t. That, that's the 125 times t. L dr over 2 pi r. I'll put the r over here. Yes? Now, what's the total magnetic flux through this loop?
The integral.
Let me call this distance A. And how about I call this distance B? So, how do I get the total magnetic flux through this loop?
Integrate from A to B.
Integrate both sides, and all of these are space dependent, right? Independent. So the only thing that varies is going to be r. So, and I integrate from r equals A to r equals B. So this is mu naught I naught sine of omega t times L. There's an L in there, and then I have a 2 pi, and I'm going to have the natural log of B over A when I do that integral, right? Can you see that? Or should I do the integral separately and show that that's that? No? No? Yes? Mary, you don't look happy.
Sorry, I was writing and thought I didn't hear the question.
Is this correct up to here, or did I do something too quickly? Did I miss a step, or should I put in a step? I mean, this is just this. All of these are constants as far as position is concerned, right? And then you have an L over there, right? And then this is the natural log of R from A to B. And that's just going to give me that. So, but I want the current, right? So the current is the EMF divided by R. So the current induced is the EMF divided by R. But the EMF is d phi dt. And again, if you want to be picky about it, you can put the minus sign in there, although right now it. So now I gotta take the derivative of this with respect to time. So what is the derivative of this with respect to time? What's the only place where there is a time dependence so that I have to take the derivative of that function with respect to time?
Is it W cosine?
Only in the sign, right? So I'm gonna get mu naught, which is a constant, times L, times the current amplitude, the natural log of B over A, that's a constant also. Then 2 pi, that's a constant. And then I have to differentiate sine of omega t with respect to t. So the derivative of the sine is going to be the cosine of omega t. And then by the chain rule, I have to differentiate the inside of this with respect to time, which is just going to give me a factor of omega. Yes? So the induced current will be that quantity divided by the resistance. So it'll be all of that, because this is the EMF, or at least the magnitude of it, divided by R. So if you want to, again, you can put the minus sign, and then you have mu naught L I naught natural log of B over A over 2 pi R, big R, that's the resistance, not a radius. And then you have an omega, and then you have a cosine of omega t. Now, the question says, what is the induced current in the loop at t is equal to 0? So you just evaluate this at t is equal to 0. Now, they're just asking me what's the current. So my answer is going to be so many amps. If I say minus 3 amps, I could put minus 3 amps, but the way that the question was phrased, I would give an answer without the sign. That sign is associated with whether it's going to be clockwise or counterclockwise, that sort of thing, the direction of that current. But at t is equal to 0, all of this would be 1, because omega sine cosine of 0 is 1, right? So the current would be, all of that, except that the cosine omega t goes to 0. So that would be mu naught, which is 4 pi times 10 to the minus 7 times L. L is this thing, which in this problem is like 8 centimeters, so that's 0.08 meters. That's L. I naught is the amplitude, which is 15 amps, divided by 2 pi R, where R is the resistance, and I think we were told that the resistance was 2 ohms. So that's convenient. This 4 pi cancels this 4 pi, so I don't have to do that, include them in the algebra. And then I have the natural log of, oh, and there's an omega too that I can't forget. So B, I called it this distance, right? I defined it as this distance. And according to this diagram, it's 5 centimeters plus 5 centimeters, which should be 10 centimeters. That should be 10 centimeters is 0.1. Although here it doesn't matter because I'm taking the ratio of two things. And A is the distance from here to there. So in this picture is 5 centimeters, so that's 0.05. In other words, this is just the natural log of 2. An omega, right? Omega is 120 pi. I forget my omega over here. And it's good that I said a little while ago, I cannot afford to forget that. So, and that'll be so many amps. That will be the current at t is equal to 0. And then it says, what is the induced current at t equals 2.1 times 10 to the minus 3? So that's at 2.1 milliseconds. So you just do this thing again. And what you have to be careful is it'll be all of that multiplied by this quantity, evaluated at 2.1 milliseconds. So what is this? That'll be the cosine of, this is 120 pi. Notice that this is in radians per second. I'll put in the units. And then the time is 2.1 milliseconds. 2.1 times 10 to the minus 3 seconds, right? So this cancels that. So what you need to be careful here is that this is 120 pi times 2.1 times 10 to the minus 3, and this is in radians. So you're taking the cosine of an angle in radians. So either you set your calculator to radian mode and take the cosine of that, or you calculate this and you're gonna get so many radians, and then you convert that to degrees, and then with your calculator set to degree mode, you take the cosine of that. Yes? And that's gonna multiply your answer to part A. Nowhere in this question do I see, like, which way would it be the, so I would just give two positive answers as an answer.